Hey folks, Todd Coburn from Cal Poly Pomona with your Aerospace Structure series. This is a sub-lecture on vector dot products. You're going to want to first watch my lecture on vector cross products. Then you'll be ready to cover this lecture on vector dot products and on mixed triple products. This is a foundational mathematical concept that is used for numerous or nearly countless mathematical operations, trigonometric operations, and engineering applications. For our purposes, we're going to find it's quite useful for statics when we're finding the projection of a vector onto another one. It also is invaluable when we're talking about three-space operations, when you're doing orbital mechanics and other kinds of three-space operations. Let's take a look at how it works. You should have already learned this back in physics, probably seen it again in calculus, probably again in linear algebra. But it's critical that you understand this for some of the operations we're going to need to do in our statics class. So review the video carefully, watch it again if you need to, subscribe to the channel so you can get other updates to the content on this. And then practice until it's yours and you're not having to work very hard to nail it every time. Then you're ready to build on this foundational tool. This is like a weapon of the trade, like a well-oiled pistol. Then you'll be ready to master statics. Let's see how it works. So we're going to start out by defining, this is called a scalar product because we're dealing with vectors, but we're going to end up with a scalar result from the vector operation. Okay? The scalar product, it's called the scalar product or the dot product. Most commonly the dot product. In math, you'll hear it called the scalar product more frequently. Okay, so if we have two vectors, P and Q, vectors have magnitude and direction. And if we take the scalar product, which is the dot product, which is P dot Q, we can do Q dot P or P dot Q. Let's focus on P dot Q. We got two vectors, and we're dotting P with Q. These vectors are at any orientation. And because there are two vectors, each vector has direction and magnitude, these two vectors make a plane. When we take the dot product, we're going to get information back regarding the angle between these two vectors. This is a very powerful concept. We're going to find out that this result, P dot Q, both vectors, gives us a scalar result, which means it just has magnitude. And that magnitude is PQ cosine theta. This means the magnitude of P times the magnitude of Q times the cosine of the angle between them. Once again, this is very powerful. A very powerful tool. For these operations, our mathematical rules are we're going to find out that they're not commutative. They are commutative, which means P dot Q gives the exact same scalar result as Q dot P. Great. They are distributive. That means P dot Q1 plus Q2 is equal to P dot Q1 plus P dot Q2, as many of our other math operations work. However, they're not associative. P dot Q dot S, this is can be undefined. So these are our rules of operation. If you don't nail these, that's not critical. We're going to learn how to use these and master them. So if we have two vectors, P dot Q, our first vector has an X, Y, and Z component. And the way we express three-dimensional vectors is we put whatever the magnitude is of the component in the X and whatever the magnitude, and we take that and we multiply it by the unit vector in that direction, right? So we commonly say px in the I direction. Py, the magnitude in the y direction, times j. J is just a placeholder that says this component is acting in the J direction, and PZ. So when we talk about vectors having magnitude and direction, we can either specify their magnitude in some angle, or we can specify them in terms of their components, Px, Py, Pz, against each of those acting against their unit vectors, the unit direction vectors, I, J, K. So Pxi, Pyj, Pzk, summation of those, expresses the vector in 3 space completely. Now, if we had a planar vector, in order to express that, a vector that lies in a plane, we would just need Pxi plus Pyj. Or we could say that it's magnitude of P times whatever angle it makes with our horizontal x-axis. In 3 space, you now need 3 angles to define that, and that starts to get ugly, and this way of expressing with unit vectors is much more powerful. So you want to master this tool, this weapon of the trade. So we have 2 vectors, Pxi plus Pyj plus Pzk. That's one vector. The other one is Qxi plus Qyj plus Qzk. This is our other vector. Once again, any or all of these magnitudes, these components, could be 0, or they could have some magnitude. That will completely express the vector. If we're taking the dot product of these, we just use that dot product operation between the 2 vectors. Now, the rules, we saw the rules for cross products in our lecture 5a. The rules for dot products are a little different, kind of like the reverse. If we dot something, a vector, with itself, something in the same direction, we're going to get 1. If we dot it against anything else, against a normal vector, we're going to get 0. So remember, I, J, and K are the 3 unit vectors along our coordinate axes, and these 3 axes are perpendicular or orthogonal to each other. So then when we have I dot I, we're going to get 1. Why? Because remember, the dot product is defined as P dot Q is PQ cosine theta. So we take the magnitude of the I, which has a magnitude of 1. So we have 1 times cosine theta. And cosine, if these are in the same direction, cosine of theta is just 1. So we end up with 1. Same thing if we have J dot J, we're going to get 1. K dot K, we're going to get 1. However, if we have I dotted with J, what this means is I is in the x direction, J is perpendicular to that. The cosine of 90 degrees is 0. So the magnitude of I, which is 1, the magnitude of J, which is 1, times cosine of 90 degrees, which is 0, that's 0. In the same way, J dot K, K dot I. So if we take the dot product of any orthogonal or perpendicular vectors, we're going to get 0. If they have the exact same orientation, if they're parallel to each other, we're going to get 1. That's how it works. Therefore, we see when we take P dot Q, we're going to get Px Qx times I dot I. I dot I is 1, so we have Px Qx left. That just did this times this. We're dotted with that, and that gave us this term. Then we take Px times Qy, which is Px Qy, I cross J, which is 0. That term is blown straight to hell. We have Px Qz, I cross K. That one's blown straight to hell. Now we have Pyj crossed with Qxi. That's Py, Qx, J cross I. That's 0. Py, Qy, J cross J is 1. We have that term here. And then Py, Qz, I cross J is also 0. When we take this term against the first term, 0, that's K cross I, or K dot I. That term against this term is K dot J, also 0. We're left with Pz, Qz, k cross k, which is 1. That gives us this term. Got it? Is that beautiful or what? So when we take p dot q, we can write it this way. We find out if then, using the same logic, if we have p dotted with itself, that is just going to give us the square of that. How? Because in this first term, this p now is px, which is px squared. Py squared, pz squared, that is just the square of the magnitude of that vector. This has countless practical applications in mathematics and in engineering. Okay? Let's go onward and look at this further. All right, so we defined our scalar product, or our dot product, as p dot q equals pq cosine theta. All right, so if we look at this concept further, we see this p and q with this theta. Okay, so what we see is we have q. Focus on these two vectors. We've got p and we've got q, and they form a plane. Okay? Now we can, if we take a look at this and we look at the angle between these two vectors, we see that actually if we draw a line perpendicular to P going through Q, the tip of Q, we find out that Q has a component parallel to P and it has a component perpendicular to P. Let's look at that. Q has a component parallel to P, that's Q in the P direction, and it has a component perpendicular to P, that is Q in the that is perpendicular to P. Got that? Two components, okay? Let me clean my screen. What this means is one component is along the vector and one component is not. The component that it shares is just Q cosine theta, right? Q cosine of theta is the projection of Q onto P. Q cosine theta is just the projection of, imagine looking from up here, and the way it projects on like a shadow is this is Q in the P direction, and it is actually the projection of Q onto P. Got that? All right. So we have one component shared, one component not shared. Since the dot product eliminates components that are not shared and only gives us the components that are shared, we can see that the component, that operation PQ cosine theta. Now, if we had gone the other way, PQ, if we look at the projection of P onto Q, if we look at the projection, so if we take a perpendicular to Q, and we look at, and this is now 90 degrees, we see this projection of P onto Q, that's P cosine of theta. And so we find out that whether we're taking P dotted with Q, we're going to get PQ cosine theta. That's Q onto P. If we take Q dot P, then that is Q times P cosine theta. One is the projection of P onto Q. The other is the projection of Q onto P. And the magnitude is lo mismo, the same. See that? Because the way we're going to write it is just PQ cosine theta. So you don't know which one, you don't necessarily have to specify which one you're dotting onto which one. Remember that that operation, order of operation doesn't matter for these guys. Okay, so we're going to find out that this is very useful for a number of things, as I keep telling you. So P dot Q is PQ cosine theta, which is PX QX plus PY QY plus PZ QZ. Now, if we take this vector, PX QX and so on, and divide this, take this piece, if we take this mamba jamba and bring it down here, then we get this equation. We find out that the cosine of the angle between the vectors is just this divided by that. This is the dot product, P dot Q, divided by the magnitude of P and Q. See that? This is a very powerful observation that we can use for a number of things. And this means we can easily project a vector using this principle. Project a vector on another vector. So here in this picture, you can see we've got x, y, and z coordinates, and we've got some other vector, OL. And we're actually defining a vector Q onto OL to make it easier. If we're trying to find the projection of P onto Q, then all we need to do, which is both the projection of P onto Q and the projection of P onto OL, all we need to do is take P cosine theta. That gives us the projection. Or we can take P dot Q, since that's equal to P cosine theta, we can see that rearranging this result says that P dot Q divided by the magnitude of Q gives us a projection of P onto Q. That means Q dot P divided by the magnitude of P will give us the projection of P onto Q. See it? The P dot Q over Q gives us the projection of P onto Q, and Q dot P over P gives us the projection of Q onto P. I think I said that backwards. Q dot P gives us the projection of Q onto P. By dividing by that P, it gives us the unit, the amount in that direction. Okay. If we have just a unit vector, we can actually find the component along that vector. Now back here, so what that means is if we take that, if our OL line of action, if we have a unit vector along the OL, which is just Q over its magnitude, right? Then what that will do when we take the dot product of P with that unit vector, then we're just going to get that axis, that projection onto that axis as well. Make sense? Okay. This brings us to one other idea, and this is the mixed triple product. Once again, you need to first watch my cross product video, unless you already understand cross products. The mixed triple product is a fancy set of words that we apply to the operation when we're taking a dot product and a cross product. According to order of operations, you're going to need to take the cross product first. So S dot P cross Q, those brackets say we're going to do that first. P cross Q is going to give us a vector. And then when we take the dot product with S, that will give us a scalar. Okay? This is used for a number of things. Once again, engineering applications, and we're going to find a couple special uses for this mixed triple product in statics. So this, if you've mastered cross products and mastered dot products, all you need to do is follow the order of operations rules, and this will work. Once again, P cross Q is going to give us a vector that is perpendicular to both. So we see that P cross with Q gives us a vector perpendicular to both. And when we take the dot product of S with that, we're going to get a projection of S onto that P dot cross Q direction. Okay? That's how that works. Let's take a look at the rest of the stuff. So S dot P cross Q means first you're taking the cross product and then you're taking the dot product. Okay? And this tells us about some of the rules. Once again, if we want to evaluate the mixed triple product, actually it's just like when we're doing cross products. You can do it all at one time. Remember, with cross products, we would have put an I here and a J here and a K here. And if we first do the cross product of P with Q, that's what we will do, and then we will take a dot product. But you can actually do it in one big bite of the enchilada by just instead first constructing your little matrix here, where we're going to first put the vector that we're dotting. We have the SX, SY, SZ, and put in our, instead of the IJK, and then perform the same cross product kind of operation. What this means is we're going to have S. Remember, the way this works is we're going to go like this. We're going to have S. So first we're going to, let's do it this way. This mixed triple product, S dot P cross Q, is going to be like this. We're going to take this first guy, SX, SX, and we're going to multiply him by this little vector here. This was SX, this was SY, this was SZ, this is PX, this is PY, PZ, this is QX, QY, QZ. So what we're going to do is take this guy and multiply it by this minus this. So SX times PYQZ minus QYPZ. And then we're going to have plus, and now we're going to take this second guy, SY, and now this little guy, we're going to just focus on these terms out here, ignore those, and ignore these. Actually, we're going to use this one. So this is the SY, and we're going to have this guy times this guy minus this guy times this guy. But this is actually a negative. So we're going to have minus SY. The second one gets a minus, and we're going to have PXQZ minus QXPZ. And then our last term is plus again, SZ. When we look at this guy, the SZ is over here. So we're going to focus on these terms, this minus this. So we're going to have plus again, SZ times, and now we're going to look at these guys, which is PXQY minus QXPY. And that is how we can do it all in one step. Is that beautiful or what? The answer to that question is beautiful, not what. Okay, so Lecture 5A, you learned about cross products. Lecture 5B, we learned about dot products and mixed triple products. Practice these, master these, make sure you can do these flawlessly so that as you're going through your statics principle, you can focus on just applying the static idea using the weapon that you have found, right? If a cowboy is in a gunfight against the bad guys, he's going to lose if every time he gets called into battle, he's checking out his gun, trying to figure out how to use the dumb thing. If you want to be a cowboy, learn how to use your pistol, and then start trying to implement justice for all, not in the other order. And that's what we got to do too. Enjoy.